Hello, everyone, and welcome to this virtual IoT meetup. My name is Frédéric Desbiens, and I'm the program manager for Edge and IoT at the Eclipse Foundation. It's my pleasure to host those virtual IoT meetups, and today we have a really interesting one. So the Cyclone DDS project is a project that we've had at Eclipse IoT for a while now. And we have the chance to have a committer on the project to tell us about all the exciting innovations happening there and introduce you to the DDS protocol if you're not familiar with. So Eric, really the stage is to you. So please go ahead.
Thank you very much. So I'll try to share my screen. We tried it. It worked not so long ago. So Frédéric, are you still there? Can you tell me if it worked?
Yes, absolutely. We see your screen. And by the way, Eric, do you prefer questions as we go, or only at the end?
No, as we go, I think, because I kind of enjoy the questions more than the fixed part.
Okay, so attendees, please use the Crowdcast chat and add your questions as you get them, and I will read them to Eric as we go, and we'll try to answer them in a timely fashion. All right, so let's get started. Thank you, Eric.
Yeah. Okay. So this is about Cyclone DDS, of course, but Cyclone DDS lives in a context that's a little bit bigger than just the one project. And the one context is the historical context, to which I will come later. And the other context, of course, is what do we intend it to be used for? And actually, I intend it to be used for a lot of different things, for mil-aero, for robotics, but also for the IoT, where I think the characteristics of DDS in general and the Cyclone DDS implementation are particularly suitable for quite a few IoT systems. Now, the key bit about IoT systems, of course, is that it's all about data. You have to get to have your sensor, your measurement systems, get the data from them, do whatever you want to do, analytics, control loops, whatever, produce the output, log data, historical data. All this happens in a dynamic context where nodes come and go, sensors come and go, participants come and go. And that's not quite a small challenge. Now, there are various protocols and various middlewares that quite adequately address a number of the characteristics of these systems already, and some of them are readily available in the Eclipse ecosystem, and QTT is a very good example. But DDS brings something special to the table that I believe is the magic sauce that quite a few people could use. So the first bit that you need in the IoT is you have all these sensors, you have all these users, there are all these components in the system, and you don't really want to have to worry about what runs where, what happens to be located on which machine with what IP address or non-IP address, as the case may be. All you really need is the data to go from wherever it's generated to wherever it's needed. As I mentioned MQTT before, it's an excellent example of a system that does quite a bit of this location transparency side. As long as you know where the MQTT broker is, you're good. The trouble with that, of course, is you need to know where the broker is, so it does require some configuration. In DDS, we have fully dynamic peer-to-peer automatic discovery as long as you have multicast. And so then you don't even have to know where your peers are. There is no broker, so you don't have to worry about the broker. So that's one part of location transparency, and quite an important one. The programming model is flexible and in ways that allow you to scale from edge systems, small sensor nodes, to what are they called? Basically data centers in the cloud, and run a cluster of machines in a virtual single data space. As I mentioned, DDS is essentially a peer-to-peer system. Now, peer-to-peer has great advantages. I mean, you cut out the middleman of the broker, so you gain improved performance typically, especially latency gets better if you take out a broker. Doesn't mean it's perfect. Obviously, if you have a client with a broker architecture like MQTT, the client can be really tiny and typically smaller than what a full-fledged peer in a peer-to-peer network would be. The DDS protocol, the DDS API, everything is flexible enough to allow putting brokers into the network, but Cyclone doesn't implement that part yet. Next to location transparency, you also want temporal decoupling. It's kind of transparency in time. You don't really want to have to worry about what nodes in the system are operational and then wait for the important ones to be ready, have subscribed to everything before you start publishing and before you start doing anything. Because, well, nodes come and go, connections come and go. There can be interference in a radio network. So nodes can break down and need to be replaced. There's all kinds of reasons why you might be late in joining the network. And so this notion that you start the system, you first start all the components on all the machines, you wait until it's ready, and then you start doing something. It works perfectly well for things that run in a single machine. It doesn't work so well for things that run in a network. Case in point, basically, is how robotic systems, ROS2 systems started at this time, or ROS1 as well. People tend to start the components first, wait until it sort of settles, and then start operating the robot. I think that's the wrong way to do it. But if you don't want to do it that way, you need to make sure that you can deal with historical data and that late joining nodes, late joining processes get the data that was already published before them if it matters to them. Obviously, security is a major issue in IoT systems. Fortunately, there is a pretty solid standard for securing DDS networks, which has been developed by the RMG, the DDS vendors, and checked by various departments of defense. And it's not present yet in Cyclone, I admit that, but that will come. And then you will have interoperable security with other vendors' implementations. And you basically get military-grade security in your IoT system, all a few configuration files away. And as I mentioned, there are other implementations. There are many implementations of DDS at the moment, and the standards are pretty decent, and there is a good cooperation in the working groups at the OMG. And so there is a pretty good interoperability between the different implementations. Every now and then it gets tested in plugfests in one way or another. And I know from the company side that the interoperability is actually being used by companies and that it works well. So what is this magic thing called DDS? It's very simple. It's an eventually consistent shared data space atop a publish-subscribe messaging system. And with that, if you are well schooled in the history of these systems, you probably know pretty much what it is like. Though it does leave, this simple statement does leave a lot of variables open that you could use or choose to implement in many different ways. So let's get into a little bit more detail, starting with the context. DDS, the standard was ratified in 2004. As you can see, Since then, quite a few updates or extensions have been done. DDS defines the programming model, like you have topics and read and write and blah, blah. And it defines the API and the way you specify your types. DDSI RTPS is the standard that defines interoperability between the nodes. At first, the implementations did not support RTPS, or they only started supporting it slowly from, I would say, RTPS 2.1, 2010. The interoperability standard is pretty decent, and everybody implements it, and it works. So with the combination of the DDS standard and the DDSI standard, you have a standardized API, a standardized way of specifying your types, and a standardized protocol to connect your processes. So basically, source portability and interoperability on a network. With X types, it gains a lot of expressive power in how you define types. The DDS, PSM, C++, and Java are really about updating the APIs to be a little bit more usable. I'll have an example of the old C API later on. I'm sure you will agree. So there is good development in the standards, but DDS doesn't come from nowhere. There is a timeline that certainly goes back. At Thales, one of the original authors of the DDS spec, to 1991, at which point the first real system based on this way of building systems was released. Or built and released a little bit later. That's a command and control system for frigates. Thales was is a defense contractor, and but they've also done other things. I mean, there is a control system. I don't know exactly what it does, but there is a control system that used to be used anyway in the subway in Amsterdam. And that was also built on the same architecture. So I would say from essentially day zero, it's been dual use and has been used in what now would be called IoT systems, arguably. Before that, you end up in 1984, the first publication of the model, and 1987, the patenting of it. The patenting is interesting. I mean, surely this must be a software patent, but as far as I know, software patents in 1987 were as good as impossible. So it's a US patent. So it must be one of the first software patents. Now, software patents are perhaps not to everyone's liking. Don't worry, this one has long since expired. But you can, given this timeline, you can definitely argue that DDS has a 35-year history or so. Now, this 35-year history is one that comes from Thales Netherlands, from Hollandse Signalapparaat, and from Naval Command and Control Systems. And there, the system really is an eventually consistent shared data space. That's all that's presented to those who want to write applications on top using it. Under the hood, it uses publish-subscribe as an implementation technique. So it's a publish-subscribe system, but you never really do the standard publish-subscribe messaging thing with it. Instead you put your results in a shared data space, and you read whatever you need from that data space. The other parent of DDS is a company called Real-Time Innovations, RTI. They had, I remember seeing the manual version, very little, one or so, or two in the 90s. They had a pure publish-subscribe messaging system. And from what I've gathered over the years, it started as an idea of how to build robotic systems at the robotics lab in Stanford, quite a few years before it got founded. So the kind of cool thing now is that they started in robotics, moved into mil-aero and all kinds of things, and now it's a major player again in robotics. So full circle for them. But Splice is the older of the two, so I suppose the more important parent. Certainly because it's my own personal history that plays there, that I think so. But those systems have similarities. Like they all require low latencies, control loops of whatever kind you need, predictable, low jitter, low latency things typically. They all have high throughput. Now, high throughput in 1990 was something different from high throughput these days. I give you a little demo. I managed to get my old SparkStation 20 up and running again. You can see the difference in performance compared to what these days would be considered normal. But anyway, for the time, it was a lot. And most of the data really gets updated frequently. It flows through the system rather quickly. All kinds of filters, all kinds of state gets updated because of the processing that's done on the data, but it's not so much about storing data. And that it really differs from, let's say, databases. And both pushed for or relied on dynamic discovery. Splice is, I would say, argue more than DDS. It looked further ahead. The goal was more ambitious. The goal was building systems that can survive any kind of failure and keep running. And so the idea of a global data space in which the state is stored and the state wherein the state is preserved, even if part of the system collapses, fails, crashes, was and how you use that when developing applications, how you have to structure your applications to get the benefits of that, was something that was important there from day one. Both parties had a problem that proprietary middleware became unpopular over time. So both had a push from the market to standardize, and they found each other at the OMG and developed a standard that basically gives both at the same time. So you get the shared data space model from Splice, but you get direct access to the publish-subscribe messaging of RTI at the time. So that went well for a while in defense, mil-aero, whatever. Lately, it's been expanding into all kinds of different fields. And so some of the areas in which it gets used these days, these are just a few pretty pictures that I happen to know about. One, smart greenhouses, where you monitor the humidity, the temperature, and everything, the soil quality, water content in the soil, and then automatically, either you just monitor it and then you decide what to do, or you could even do a fully automated system that simply adjusts the rate of irrigation based on the actual humidity and sunshine. Air traffic control obviously gets used for adaptive optics in the European Southern Observatory. Fujitsu is a big user in software-defined networking and really high-end telco switches. Robotics in the form of ROS2, yes, but also proprietary systems like this one that's a cow milking robot. So the cow walks there, gets recognized, and gets milked automatically. NASA has used it for doing telemetry and sending at the Space Center for the launch. I think RTI's products has made it to Mars even. So train control systems, farming equipment gets used in all kinds of different contexts these days. Now, these are all a little bit on the big side. These are not really your average small device IoT systems. And that's a little bit of a problem that something needs to be done about, if you ask me. Okay, so this is all good. We have this cool system. It gets used in all these contexts. It's a shared data space, but subscribe messaging, okay. But as I said, there are a ton of different choices you can still make. And so in DDS, those have been made. You define your types, then you create topics. You're free to create as many topics as you like, and each topic actually has a type. Those exist as are inert objects. You have to publish data for something interesting to happen. So you create a data writer that has a specific topic, and it allows you to publish data of that topic. And there are data readers for a specific topic. And if the reader and the writer have the same topic, the data goes from the writer to the reader. And if the QoS settings have been chosen well to store, to retain the data, then the middleware will retain the data as well, so that the late joining reader can get it. That retention gives you the temporal decoupling. The fact that you only work at the level of topics means you get spatial decoupling. This is, by the way, not much different from, let's say, MQTT. The only real difference at this level of abstraction is that there is no broker. There is no single point of failure. Data from different topics flows. If you have 4 machines in the same network, then it can easily be the case that you have data flowing from A to B and data flowing from C to D, and they never even interfering with each other at the network switch. So you have a lot of decentralization, and that's good for fault tolerance and also for scalability, given a system, given a certain network. So, as I said, topics are named, topics have a type that you define. There are also the QoS policies, and those QoS policies allow you to specify all kinds of things. There are a ton of QoS policies. The key ones, of course, are like reliability. Do you want, are you okay with data being lost in transit, or do you really want to receive everything that you've written? There is history. Do you merely want the most recent value, or do you want everything like an ordinary queue would do, or would you like the most recent 100? You have you can designate key values in the data. If you say this field or these fields together are the key, just like in the primary key in a relational database, then it will those histories that like if you say the most recent one, but then it will be the most recent one for each key value separately. So you have those. Then you have the durability setting, which allows you to say the data is send and forget, or the data should be retained while the writing process still exists. Or you can say, I want the data to be retained even if the original publisher is gone, and so on and so forth. You can do filters on content, filters on time. You can specify limits on how long the data should remain alive, etc., etc., etc. You have tons of QoS. And then the final bit, I would say, is that the built-in discovery, the essentially zero configuration discovery means that your network forms automatically. Now, if you don't have this works beautifully if you have multicast. Everybody multicasts his presence, and then you build up with address information, and you build up from there. If you don't have multicast, or either because your network doesn't support it, or out of choice or whatever, then there is no problem. You will simply have to specify some addresses to bootstrap the discovery, and at which stage it's quite comparable to specifying the address of a broker. There are many implementations, as I said. There are many platforms on which it runs. There are many languages that you can use in combination with DDS. And all of this is Interpol. So that's nice. Now, Cyclone, finally we get to the meat of the matter. Cyclone is a completely new implementation, as a DDS implementation goes, but it reuses some trusted and proven components from OpenSplice. In particular, it reuses the networking stack from OpenSplice. So even though it's only a year old, it has seen its fair share of abuse in the real world. Why did we do this? Well, we think the current open source offerings are not a good fit for the IoT market. There are a number of them. You have fast RTPS. You can argue that fast RTPS is not a real DDS implementation, but merely a DDSI implementation, but whatever. In any case, it doesn't implement a lot of the functionality of DDS. So and yet that functionality, I believe, is important for IoT systems, like having access to historical data. So that one, for example, is lacking in functionality. It's also not so performant. Okay, that may not be a real problem. There is, for example, OpenDDS, which has a huge footprint. So if you want to run it on a small machine, it's not going to work nicely. There is the OpenSplice Community Edition from AD-Link that I work for, but it's the Community Edition is a simple code drop. It periodically gets updated, but it's not an open development, and it's also has a pretty large footprint. There is also in many implementations, probably not even merely open source implementations, some optimizations that are lacking, that are quite important, and one that's missed in many implementations, not in all that I listed, is optimized intra-process communication. So if you have a process, if you have a node, one machine, and you decide to put all your functionality that has to run in that machine in a single process, but you still want to develop it as all kinds of small microservices, and you just amalgamate them in the executable, you would like to keep using the same API, publish and subscribe, read and write normal way, and yet have it optimize the data transfer from the local writer to the local reader. I mean, you're in the same process, you can just flip a pointer, that's all you have to do. But there are some implementations that would copy the data through the network stack, even in that case. So obviously, I don't think that's a smart choice. And so these are things that we try to address in Cyclone. Now, another bit is that we've observed that DDS is not very popular in IoT systems. I looked at the developer IoT survey, IoT developer survey from the Eclipse Foundation. Unfortunately, this is 2018. I couldn't find exactly this graph for 2019. But as you can see, there is MQTT, which is used a lot and very popular, and there is HTTP and HTTP2 and WebSockets and all kinds of things. Eventually, you end up at DDS, and yes, we're growing, but we're still below 5%. We were still below 5% in 2018. Now, if you ask me, there are real benefits to using DDS more than merely 5%. It's never going to cover all cases, but there is a sufficiently large group of cases of systems where it would be useful. And still, it's only at 5%. And our guess is that part of it is complexity of DDS. It has a higher barrier to entrance than, let's say, MQTT. And in part, it's that the availability of open source implementations is just not quite what it should be for that adoption to happen. So with Cyclone, we have one that's developed in the open. I mean, the Eclipse Foundation guarantees that. It's small, it's performant, it has the optimized things. It's not done yet, so there is some functionality missing at this point, but that is being added. So what do I mean when I say it's performant? This is a measurement I did on my own laptop over the loopback interface, so it's kind of cheesy. Some months ago, but the numbers are still, as far as I know, all the numbers are still valid. You can see all the disclaimers, the details in the disclaimers, but for small messages, you can see Cyclone is over 1 million samples per second. soon as you have slightly larger messages, you're at ridiculous throughputs. Latencies are really small. This graph doesn't include latency. And it's an order of magnitude or so. No, not quite an order of magnitude above its nearest competitor in this very carefully chosen set. The open source implementation supported by ROS2. I don't know how it relates to, let's say, RTI's offering. I don't know how it relates to TwinOak's offering. Those are commercial products. I cannot test them. And even if I could test them, I cannot give benchmark results. But if I mentioned earlier that fast RTPS is perhaps a little bit lacking in performance. Well, you know, I think the graphs tell that story better than I can put it in words. From the README, from the front page of the GitHub repository, I copied the Linux over gigabit Ethernet graphs. This is using hardware from 2012, so it's not extremely high-end hardware these days anymore. If you look at it, saturates the network at about 2 kilobyte or so, 1 kilobyte samples. It manages 1 million samples per second reliably over gigabit Ethernet. And it has a latency that's, 30 microseconds or so end-to-end if the messages are small. It's there is more details available on the website, but in any case, the short story of it is for really small messages, it's still CPU bound. Take a faster machine, probably take a modern high-end machine, probably it will go a little bit faster because the CPU performance will have improved a little bit in those past 7 years. But that's one area that I fully intend to improve performance. Unfortunately, I don't have 10 gigabit networks, so I can't show you what it would do over 10 gigabit. I don't even know myself. Wi-Fi, I don't have decent Wi-Fi measurements, so but I know Wi-Fi is being used in some roving, some autonomous vehicles recently, and reports are that it works well. So for what that may be worth. And the footprint is small. I mean, you can argue many ways. In the fine print in the graphs, the gigabit Ethernet graphs, it said our resident set size is below 10 megabytes for all those measurements. If you add up all the memory it allocates and you really try to squeeze it, and there is some runtime configuration things and there are some compile time tricks you can do, you can get it to fit in 1 megabyte of memory, even though it runs a tiny little bit slower if you do that. But hey, if you have performance to spare, you can afford to waste a little bit in gaining or in reducing your footprint. There are no real dependencies on other libraries, and so it doesn't support, well, it only technically supports Linux, Windows, and macOS in the sense that those are the three platforms that we build it on in the continuous integration system, and we really require that it works. But we know it works on FreeRTOS, and we also know it works on Solaris 2.6. Which is just my own pet project. All the core DDS functionality is available today, and it works well. I mean, there are, if you look at the issues on GitHub, there are some, but most of the things that are there it's more like questions than real bugs that people run into. But yeah, of course there are some bugs, but it's pretty reliable as it is. Some things are missing. I mean, the DDS defines profiles. You can have the minimum profile, or you can do content filtering, or you can do blah, blah, blah. It's not strictly the minimum profile subset of DDS, because some QoS settings haven't been implemented, because the focus has been on getting the core functionality to be really reliable. And something like automatically deleting a sample if it's more than 10 seconds old is something that sits on top of the core protocol implementation, the core machinery, and so is relatively easily added later. And as in my experience, it's really rarely used anyway. And the key things that need to be added are full support for transient data. Without that, it's not a shared data space that I like so much. Security, which is being worked on, needs to be added, and the extensible types need to be added. Once you have those, you really have a full functional DDS implementation that can compete with with all the commercial offerings that you can find. So it's quite a manageable amount of work. I may have cheated a little bit in saying that would give you something competitive with all the commercial offerings, and the problem is in language support. Today, Cyclone, and this is a deliberate choice, it only has its own unique proprietary, as it were, C API. The reason is that the standard C API is a pure translation of according to following the IDL to C mapping of the original IDL in which the original interface is specified, and it's a total usability disaster. You really don't want to be programming using that API. So given that this is a native pure C implementation, you need a C API. And if you have a good C API, you can build all the other language bindings on top of that. But you also want that C API to be nice to program in. So that was a deliberate choice, and there is a lot of effort, a lot of hours go into supporting many different, or implementing all these different language bindings. So again, the decision, the focus has been on quality and performance of the core functionality, and not so much on fancy language bindings. Those will be added. I know that the new C++ API of DDS, the one I mentioned, pointed out earlier, it's basically up and running. It's just not available to anyone yet, unfortunately. The old C API, I'll probably add it one day, because there is even though that API is as good as unusable, there is a lot of software written using it, and adding that language binding, that API to Cyclone, will allow the existing code to be ported to Cyclone, and so that would immediately open up a lot more areas where Cyclone could be used, and that would be good for the project. Other language bindings like Python, Rust, Haskell, Ada, yeah.
A quick question there, Eric, about this API situation. So when you say the standard C API was not very good, that kind of stuff, so is that standard API part of the DDS specification? Who designed it, essentially?
It's part of the DDS specification, but I don't think it was designed as such. I think that's the whole problem.
Okay.
DDS is specified in the DDS standard specifies the interface in OMG IDL, the interface description language that dates back to Corba. The OMG back in those days, so that's early 90s or something, also specified mappings from IDL to different programming languages. So there is a mapping from IDL to C, from IDL to Java, from IDL to C++, to various other languages. And it tries to faithfully map the features of IDL to the other language. And so you have IDL supports, let's say, exceptions. It's a bad example because those aren't used in DDS. But in any case, IDL supports exceptions in remote method invocations. Therefore, the IDL to C mapping is done in such a way that you can deal with exceptions. But C doesn't natively have exceptions, and you would do it completely differently if you design the API for C. But because of this mechanized transformation from IDL to the programming language, you end up with something that's just unnatural. Mm-hmm. But the operations are fine. I mean, there is read and there is write and there is take and create data reader. That's all fine. It's just the details, how you plumb this stuff together, that's a little bit of a disaster. So the newer APIs, the new C++ and the new Java API, those have been designed taking idiomatic C++ into account. So those are fine. It's merely the automated transformation from IDL to whatever programming language that's painful. I mean, it has its advantages, right? You can take the IDL and write a small preprocessor that generates JavaScript or that generates foreign function imports for Node.js, and boom, suddenly you can use DDS from Node.js. And I mean, I tried this, and it takes like 500 lines of Perl script, and there you go. You have an API that you don't want to use in JavaScript because it's the exact same problem, but it's a neat feature that you can do that. So I think there is value in having both, but you can build one on top of the other. And so the choice of Cyclone is give it a good C API that's easy to use, and then put the other APIs on top of it. We keep the API stable. I mean, I think there have been no significant changes to the API in the past year. There are a number of things that need to be improved or fixed. So those will be done in one big go in the not too distant future. But otherwise, you have this stable interface, which is perfect for building all kinds of systems on top of it.
That makes sense. Hey, thanks a lot.
Yeah. So I just concocted the most trivial example. It's a simple hello world, a publisher that publishes it hello world at startup, and then every 10 seconds. Why every 10 seconds? Well, I made it transient local so that if you join later, if you create your reader later, you get it immediately. You get the most recent sample immediately. Subscribe, blah, blah. The type definition, as you can see, it's kind of like sort of C++. This is OMG IDL. The set of modules, this simply matches what ROS2 uses. And so if you publish this type with the correct topic name, you can you can create a subscription in ROS2 and get the data. So then you have to create your program. Well, you have the participant that you have to create. That's your entry point to the system. You have to create your topic, obviously. You have to set a QoS. And as you can see, that's just a few straightforward lines in this API. The std messages msg DDS string desk blah blah is what comes out of pre-processing the IDL. The publishing then simply means you have to create a writer and you have to write whatever you want to write. So that's pretty straightforward. And this, remember, this is just plain C, no fancy templates and nothing. So strategic use of void pointers, of course. Subscriber is similar, but there you have to worry about how you want to decide when to read. I chose here to say I create a reader and I create a wait set. The wait set is like what in Unix, it's a bit like selecting in Unix or Pol. You attach a number of conditions that you're interested in, and whenever one of those conditions trigger, the wait set triggers and the wait call returns, and then you can do whatever you want with it. So this sets up a wait set with the reader attached to it, and the reader has a status mask, and this says if there is data, if fresh data arrives since the last take or read, notify me. So then you go into a simple loop that says wait until something happened and read as long as there is something to read. I don't want to worry too much about memory allocation, so I just say take one sample, return it, and deal with it. Right? So that's not so hard. I don't know if you can read it. This is the translation of the exact same program into the standard C API. You can just literally follow it step by step, and all the same things happen, but you just have all this extra fluff in there. You have all the names to create a type safe interface that drives you mad, and under the hood it all maps to 5 pointers anyway. You have to, where Cyclone says the topic QoS is the determining factor, and you just inherit from the topic unless you override it. DDS doesn't do that. You have to do it by hand, even though it's the most logical thing to do. Like simply attaching a reader to a weight set that you can do in Cyclone, you cannot do that in the official API. You have to first get a status condition, because the official IDL says a weight set operates on conditions, and a reader is not a condition. A reader is an entity. So the two are equivalent, but I think it's fair to say that the Cyclone API is nicer. And then CMake is trivial, as you can see. So I can run this little program. I can try it. I don't know if I have time.
Yes, we have about 10 minutes left, so plenty of time to.
Let me try to show that. I have not set anything in the environment. I've just there is a predefined multicast address and a predefined port number to use for bootstrapping discovery. And so all I need to do is start my publisher program, and it starts publishing Hello World. Now, here, still logged in. This yellow window is a SparkStation 20 from 1995, where it's if you say you can run it on small machines, then it also means you have to be able to run it on old machines, right?
Yeah, that makes sense.
and so it has a 10 megabit Ethernet, and it's a bit slower, and it takes a while to discover it. But as you can see, it receives the data. It prints the time since publication in parentheses. So obviously, if it publishes Hello World once every 10 seconds and you got it after 8.2 seconds, it means you got whatever happened to be the most recent value published. And after that, 0 seconds, cool. So that's nice. As I said, you can also, where is it? Here. I can also start a ROS2 listener demo, and it subscribes to the same topic as my little demo program. And there you see the data as well. And so the listener is running on my Mac, the ROS listener is running on my Mac, the publisher is running on my Mac. The first subscriber was on a different machine. And this is all the configuration I need to do. So what else is there to demo? Well, there is the obvious cool thing to do. Just started testing throughput. Now, there are no subscribers, so it's just running freely, and so 2 mega samples per second or something. As soon as I start a subscriber on the old Sunberg station, you can see this little tool prints the nodes that it sees joining, and so you can see the discovery working, and then suddenly it's a queue and it's reliable, so the sample rate drops down from 2 mega samples per second to 3 kilosamples per second, but so be it. That's the consequence of having a very slow machine in the network. And as soon as I stop the Sun workstation, the publisher notices and basically goes straight back to its old 2 mega sample per second. So I think that's kind of a nice, where's my window? Here. A nice, in a nutshell, ease of use of Cyclone as a publish-subscribe messaging system and as a proto shared data space system. It's proto because the transient data support is not fully there yet. So finally, I've mentioned ROS a number of times. It's the robot operating system, and it's been around for quite a while yet. ROS 1 was ROS2 is a complete rewrite of the earlier ROS1 to address a number of troublesome issues in the ROS1 architecture. In particular, also that it, it used TCP and a broker for its communications. And robotics is an inherently real-time business, and TCP is not so good for that. And so they wanted to do something else. They looked at the various options they had, and they said DDS is actually offering what we need. And so they chose to switch to DDS, but they put in a layer in between, a middleware layer in between that abstracts from DDS. And so there are now a number of different middleware implementations that you can use in combination with ROS. Basically all the DDS implementations support ROS, but there are also a number of other ones. So that's nice. And these days, and this is still reasonably fresh, ROS2 works really well over Cyclone, to the point that we got our first endorsement a couple of days ago. The new navigation stack on ROS2 was tested on all different supported DDS implementations, and it turned out that Cyclone beat the others by a good margin. So I'm kind of proud of that. Feel free to look at, there's a cool video where you can see them starting up, and just don't blink. The Cyclone one is over so quickly that you might miss it. Finally, a few words about where we want to go. So obviously, functionality needs to be added. And I would say the 4 key bits, I mentioned them before: transient persistent data support for retaining data longer than the original writers remain in existence. Adding the missing parts of the QoS support, like lifespan that says deleted after a little while, or deadline that says, I promise I will write this every 10 seconds and notify me if that doesn't happen. Things like that. DDS security, as I said, that's being worked on. X-types is, I don't know. I don't know if it's going to make it in the next 6 months, but I think the first 3 will happen in the next half year. Another thing that we really want to do is exploit time-sensitive networking. That's kind of a new standard in Ethernet. Basically, it means you make sure that all your nodes in the network are really well synchronized in their clocks, high-resolution clocks, and then you create a schedule that says this node can send for this many milliseconds at a time slot. You do that globally. You upload that into all the hardware, and after you've done that, if you have a suitable real-time operating system, you get extremely deterministic latencies in the network, which is really good for all kinds of control systems. We're also working on reducing the dependence on dynamic memory allocation. There are more ambitious goals to actually get it to a state where you can use it for safety critical systems, but that's kind of like a stretch goal for 6 months. That's probably more like a few years' work. But certainly reducing the amount of dynamic memory allocation that takes place inside the implementation is a very good first step. And it also means that you can safely run it for non-safety critical things on really small machines. Zero copy support is a similar, is something that's, if that really works well, then you can transfer huge amounts of data over fast networks using very simple machines, very simple CPUs. And so the goal is to be able to run it on a Cortex A3 or something like that, possibly with a little bit of extra DRAM, and then still saturate a gigabit Ethernet or something like that. And then there are the language bindings that I mentioned. And for those who've been following it a little bit, we haven't been so very good at doing regular releases. And so getting better at doing that is also a goal for the next couple of months. And with that, I'm at the end of the presentation. Thank you very much.
Hey, thank you so much, Eric. So if any attendees, if any of you have questions, please put them in the chat and I will relay them to Eric. I have a question while people maybe are thinking to their questions. So you talked a lot about Cyclone DDS and the traction it's got in the ROS2 ecosystem. So are you aware of you discussed usages of DDS as a protocol earlier in your presentation, but who would be the most or the largest consumers of Cyclone DDS at this point in time?
That's hard for me to say. I think the best visible one is ROS2 based.
Mm-hmm.
Like there are a number of indications that it gives you a smaller footprint, lower latencies, less CPU use than the alternatives. And I know, that really matters for some robotics applications. And there are some manufacturers of household appliances have looked at it and said, "Oh, this might be something." So I have a very good feeling about it getting some use soon in real applications in that space. But and certainly that endorsement from the navigation stack developers won't hurt either. The reason why I say I can't really say is because there are sometimes questions on GitHub, or people run into problems, and it appears that there are some real projects out there in the world using it. But well, they're welcome to use it, and they don't have to tell me who they are or what they do, right? So I don't really know how much of a usage that is today, or will be tomorrow. So.
Yeah, and that's partly the problem with open source projects. I mean, people download your stuff and they won't necessarily come back to you unless there are problems, and then they complain.
Well, yes, and so I know the quality is pretty decent. I mean, so maybe there is a ton of people using it, and they just downloaded it, they tried it, and say, "Oh, fine, it works," and they never push the envelope hard enough to run into problems, because I can guarantee you there are plenty of bugs. It's just that they're
absolutely
getting better and better at hiding in dark corners, and only showing up when it's most inconvenient.
Yep. So we've got questions from the audience now. So a question by Arun Rao. How does Neuron SDK add business value to customers over Cyclone DDS for ROS2?
Interesting question. It's actually, I haven't really given any thought to the problem of wondering about commercial value. Of course, as a company, we sponsor this development because we believe in the end we will be better off because of it. How that exactly translates to the Neuron SDK, I really don't know.
So maybe that would be a topic for follow-up from somebody in sales.
I think so.
I'm quite sure they have a story there.
And I'm happy to take. I mean, if my email address is easy to be found, right? So I'm happy to get the question and try to forward it to somebody.
In any case, this really shows how focused on the open source implementation you are.
Yeah, well, there's only so much you can do at the same time, right? If you want to do
absolutely,
I want to do it as well, so.
Then we've got another question by Scott Lemon. He's asking, I'm just being introduced to DDS. I'm curious. So is DDS oriented towards PAN, LAN, or WAN applications, or all of those?
Historically, without a question, LAN. It's a programming model that goes beautifully on paper to gigantic wide area networks, because the programming model says you have these topics and you just read and write and whoever needs it gets it. But once you start wondering what that means if you have a million nodes, well, there are implementation choices you have to make. And so the historical focus of all implementations has been local area networks. I would say personal area networks probably come out really well. Those might have a little bit less bandwidth available, but then also not less data. So I think the smaller than LAN cases also work kind of automatically. Wide area network, there is various vendors have various different approaches to, but it all comes down to having effectively adding brokers into the network. So you create one node that subscribes on behalf of the rest of the world and that republishes what the rest of the world publishes that is of interest to you, and then those routing nodes share discovery information, and that way you can build out to wide area network scale.
Okay, and if we think about the connectivity aspect of things, so did you evoke that Wi-Fi, for example, could be working well? So did you try it with, let's say, more exotic stuff like Zigbee, LoRaWAN, those kind of stuff?
No, I haven't. I think Zigbee and some of the other really low power networks tend to have really small packet sizes. Although I think Zigbee may have raised it a little bit. And there is a standard in the DDS family, which is called the Extremely Resource Constrained Environments standard, or DDS XRC, DDS for extremely constrained environments. That process was started specifically because the default mapping of the DDSI protocol to packet formats doesn't fit so well with the really low power systems and the constraints they impose. So far the idea has been to not really focus on those networks and use an adaptation layer to make that work.
Okay, so you have a kind of gateway that will bridge the traffic then.
Yes, but when you look at the actual message formats, there is definitely a way you could reformat the message headers and make them much smaller, especially if you know that you're in a small personal area network and you know that there is this many devices, or you can pre-configure some things, or maybe discover it once and then never resend again, because like a reader or a writer is identified in DDS by a 16-byte GUID. That's a formidable amount of data if you have only 127 bytes of payload in your packet. But in that Zigbee or similar network, you don't really need those full 16 bytes to uniquely identify a node. So there are adaptations you could make to the actual protocol format without touching the core mechanisms that decide what to write or when to write or how the API works. So there is definitely something interesting that can be done in that area.
Yeah, that makes sense. Now, another question, follow-up from Scott. So he's asking, what is the discovery process that is used for writers and readers to participate in the data space, so to speak?
The discovery is split into two phases. The first is called participant discovery. The participant are the entities that kind of connect to the domain or that form the domain. And so participant discovery is typically based on multicasting your own a description of yourself, like GUID and port numbers, addresses that you're reachable on, and also a set of bits that indicates what readers and writers you have available for doing the second phase of the discovery. And then the second phase of the discovery is built on the regular DDS protocol using regular transient local data, so data that's just available to late joining readers, like my little demo program. And and so essentially, when two participants discover each other because of these initial multicasts and the responses to them, they create the matching readers and writers that they know must exist because of this little bit of information that's in the participant discovery packet. That creates matched pairs of readers and writers for descriptions of readers that exist and descriptions of writers that exist. And then the ordinary protocol mechanism for getting historical data to the late joining reader is used to transfer the descriptions of the existing readers and writers, and any new readers and writers that you create simply get pushed out as fresh data. And those descriptions include the topic name and the type name and QoS settings and type definitions potentially. So given those descriptions, you then do the matching locally between the readers and writers that you learned from the other participants and the readers and writers that you have locally. And both sides do that, and both follow the same rules, so both come to the same conclusion. And that establishes the links between the actual readers and writers. And then what address you use to send the data, that's pretty much left open to the implementation. You specify as a reader at what addresses you're willing to receive data, and what addresses you're listening for data. If you don't say anything, then it's assumed it's the same as the participant. And similarly, as a writer, you simply say, if you want to send me an acknowledgement, send it here. So then you end up with typically a writer that's matched a bunch of readers, and the readers all have unicast addresses and may have also multiple unicast addresses and multicast addresses. And then it's up to the writer to simply pick a good combination of addresses to send the data to. So a good implementation would minimize the cost to the network. But that's a quality of implementation issue.
That makes sense. All right. So last call for questions. If there are no other questions, well, the only thing left is for me to say thank you so much, Eric, for doing this presentation today. Really, really appreciate it. Thank you all also for attending this broadcast. We are always on the prowl for new presenters. So if you work in IoT and you have stuff to share with this community, well, please feel free to contact me and we can organize something. Well, I'm already in the planning stages of other meetups, but we don't have any confirmed dates at this point in time. So please keep an eye on our webpage on meetup.com to know when the next one will be. So once again, Eric, thank you so much. And
thank you very much for having me and allowing me to promote my little pet project.
Well, it's an interesting tech, and really, I mean, we have the chance at Eclipse IoT to have so many healthy projects with innovative approaches to real world problems. It's always a pleasure to work with you and the others at the link as well. Don't hesitate. Also, if you are an attendee and want to hear about something, let us know what could be a good meetup for you, and I will try to locate speakers to fulfill your wishes. In the meantime, well, thank you so much again, and I look forward to the next meetup, hopefully in a few weeks. So thank you.
Okay, thank you very much, all.